Hi everybody. In this week's video we are going to talk about the week 6 topics in Physics 112, which include electromagnetic induction, magnetic flux, Faraday's law of induction, and Lenz's law. So the first concept we're going to talk about is electromagnetic induction, which is essentially the ability of a magnetic field to create a current inside a conductor. So we already know that the opposite is true, that a current can produce a magnetic field. And we've seen this in the diagram below. If we consider a wire and we have a current traveling in that wire, a magnetic field is going to wrap around that wire accordingly to the direction of the current. So the question is asked, how can a magnetic field produce a current? Well, this current is produced as a result of changes in magnetic flux. So we're going to talk about magnetic flux next. And magnetic flux is essentially how a conducting material, or any material for that matter, is affected by a magnetic field. So magnetic flux is measured as the product of a magnetic field strength and the area of the surface penetrated perpendicularly by the magnetic field. And so the word perpendicularly is used because when the magnetic fields penetrate the surface at an angle that is perpendicular, the magnetic flux will be at its greatest value. So we're going to see later how when these magnetic fields penetrate on a surface area in parallel, there will be no magnetic flux. So the equation below is given for magnetic flux, and it's just essentially B, which is the magnetic field strength, times A, which is the surface area of the object in question, times the cosine of angle theta, which is the angle of magnetic field penetration. So the question is, how is magnetic flux relevant to electromagnetic induction? Well, we've already stated that a change in this magnetic flux will induce an electromagnetic induction. And this was postulated by Faraday. So in Faraday's law of induction, we see how a changing magnetic field induces an electromotive force, or EMF. And this electromotive force will give rise to a current. So the answer to the question earlier is yes, a magnetic field can induce a current. So both of these are true. A current can produce a magnetic field, and a magnetic field can produce a current. So we can use the diagram below to help us visualize Faraday's law of induction, which states that a change in magnetic flux will result in electromagnetic induction, or an induced EMF. So if the end result is electromagnetic induction, we can see how a change in magnetic flux will result in the creation of an electromagnetic induction. So we can use this diagram to help us visualize Faraday's law of induction, which states that a change in magnetic flux will induce an EMF, or an electromotive force, which will give rise to a current. So that is how a magnetic field can give rise to a current. So if the end resultant is the electromagnetic induction, we can change the magnetic flux in order to create the electromagnetic induction. So we can change this magnetic flux in one of three ways. We can change the magnetic field strength, we can change the surface area being penetrated by the magnetic field, and we can change the angle of magnetic field penetration. So the first scenario that we have below is we have 4 magnetic field lines traveling perpendicularly through the surface area. So this will give us a certain magnetic flux. So if we were to change the number of field lines traveling through the surface area, as we have in the second scenario, then we are going to increase the magnetic field strength. And so like we said, if we are changing the magnetic field strength, then we have to change the magnetic flux. So this will result in a change in magnetic flux, which will therefore create an electromagnetic induction. So in this third scenario over here, what we're changing is the rotation of the object. So we're changing the angle of magnetic field penetration. The magnetic field strength is the same because we have 4 field lines for each, but the angle of penetration is changing, so that will result in a change in magnetic flux, which will therefore cause an electromagnetic induction to occur. And in the last scenario, we are changing the surface area and we are changing the angle of magnetic field penetration. So the surface area being penetrated has obviously decreased because now we only have 1 magnetic field line traveling through the surface area, whereas in the first scenario we had 4. And additionally, the angle of which this magnetic field is penetrating the surface area is essentially 90 degrees, because we want to consider it as the angle between the normal and the magnetic field. So if we have cosine of 90 in our equation, that's going to give us a value of 0. So that shows us that if we have an object that is parallel to the magnetic field lines, it's going to give us it'll give us a 0 for the magnetic flux. So we can consider this induced EMF as the following equation. So an induced EMF is equal to negative n times the change in magnetic flux divided by the change in time, where n is equal to the number of turns and delta phi, the Greek letter phi, is the change in magnetic flux. So we can calculate the average value of EMF using this equation. And many people often get confused with the reason why there's a negative sign in front of this equation. And basically this just tells us that we need to consider the direction of the EMF, because the electromotive force is a vector value, so it has a direction associated with it. So now that we understand how a change in magnetic flux can induce a current, as it induces an EMF, which gives rise to the current, then we can ask the question, how do we know which direction that current is going to travel in? And Lenz's law tells us that an induced electric current flows in a direction such that the current opposes the change that induced it. So this change is the change in magnetic flux. So we can use the right-hand rule to identify the current's direction. So we're going to consider the following diagrams. We can visualize a loop here on the left, and we have a certain value of strength for the magnetic field coming upward through the loop. So from this first image to the second, we are increasing the magnetic field strength traveling upward through the loop. So we know that if we change the value for magnetic field strength, which we are doing, we're increasing, then we are going to induce a current. So that current, once it's induced, as we know from previous weeks, that current will induce its own magnetic field. So the magnetic field that is induced by the current is going to oppose the magnetic field change, shown from this first image to the second. Meaning that if the magnetic field strength is increasing upward through this loop, as we see, it's increasing upward through this loop, then the induced magnetic field from the current is going to oppose that change. So if we are increasing upward the magnetic field strength, then the magnetic field from our induced current is going to oppose that. So that's represented here, where our B value, our magnetic field induced by the current, is traveling downward to oppose that change of increasing magnetic field strength upward. So we know that if we need our magnetic field to travel downward, then we're going to have our current traveling clockwise. Because these magnetic field lines are traveling through the loop. So we want the current to have a magnetic field that will oppose that, so it will travel opposite in the loop. So that's how we understand that the induced current will travel clockwise direction. So like I said, our change was an increasing strength in magnetic field flowing upward, and an induced current will move in the direction for which its magnetic field will oppose the change being made. And when we use the word oppose, I want to make sure that it's clear that oppose does not always mean the induced magnetic field will be in the opposite direction of the original magnetic field. For this situation above, we had an increasing value of magnetic field strength traveling upward through the loop. So we needed to oppose that change, so we needed magnetic field traveling in the opposite direction through the loop. So that's why that the two magnetic fields were in opposite direction. However, if you had a situation where you had a decreasing magnetic field, so let's draw that here. If we had a decreasing magnetic field, so let's say this magnetic field was very small, then we're going to want the current to travel in such a way that the magnetic field strength inside that loop will once again be made stronger. So we're going to want our thumb in the direction of the current. We're going to want our thumb traveling. We're going to want our thumb going this way, so that our current can travel counterclockwise, and our magnetic field strength, our magnetic field from the induced current will compensate for these decreases. So now that covers everything for this video. So if you have any questions, go ahead and leave them in the comments, and feel free to subscribe.